This is video 6 in the test 2 review. I think this will be the last video. And what we want to cover in this last one is to consider the case where you're given the Bode plot of a transfer function, h of s. All right, and I'm going to draw it as a straight line approximation here. Okay, and I'm going to do basically simple poles and zeros, but be warned that you need to be able to deal with a second order. Need to know second order, in other words, with resonance. Okay, maybe I'll say something at the end. I'm not going to work a full problem though. So let's say that we have here a gain of, let's say this is 20, maybe we'll make it in dB. So this is 36 dB, 26 dB, and this is 50 radians per second. So the idea is that you're going to be given a plot that has enough information on it so you can identify like the breakpoints and the different asymptotic values like 26 dB, and then if this goes down to let's say this will go to 100, 200 radians per second. Okay. And you're asked to find h of s. Okay. So the first thing that you would want to do is, in this case, look at the pole zero plot and see if you can identify, are there poles in the system, are there zeros? In this case, there are no finite zeros. There are, I'll take that back, there is a finite zero. There is a pole at minus 50, okay, right here, pole, and there is a zero right at 200, right, because we're going from a slope of minus 1 to 0, so we've increased our slope by 1, so we have a 0 at minus 200. Okay, so right away that allows us to write the transfer function form. You always want to remember there's going to be a constant out front, or could be. And then we write our pole, which is going to be our s plus 50, okay, because the pole is actually at minus 50. And then our 0 is at 200. Now we can look at, well, what does k need to be? And for this we can consider h of s equal to 0, which in this case is going to reduce to k. And this has to be equal to the 26 dB. Well, actually, it's going to be equal to 10 to the 26 over 20. All right, got to take the anti-log of that. And that should turn out to be approximately a factor of 20. So h of s in this case is 20 times s plus 200 over s plus 50. Okay, now what if you did have a case where you had a transfer function that involved, oh, I'm sorry, I'll just say we had a magnitude response that looked like this. Okay, so we'll do it this way here. Okay. All right, this is, we'll say 0 dB here. This is really a poorly drawn one. Let me redraw it like this. Okay, and we'll have it go, take a dip, like that. Okay. And we'll say this goes down here to minus 20 dB. All right, what is this? Well, because we're going, and this presumably it would be scaled, you would see that this is going to be a +2 slope. Again, we would have to, we tried to do a pole zero plot, and although we could identify that there are going to be two zeros, okay, where are they? We don't know exactly where they are, although it looks like it's right around 100, okay, but we would be wrong to say it's at minus 100 and we have two poles here, because there is obviously resonance going on because of this non-monotonic magnitude plot, right? It's not just going from flat to going +2. It goes, takes a dip down first. Okay, so this should be indicative of something resonance that's going on. Now, clearly, in the end, it's going to be, there are going to be two zeros. So what you would do is you would say, okay, I have some s plus, let's write it this way, s plus 0, 1 times s plus 0, 2. Okay, and I'll put a constant out there because I know that, well, I can even do better than that. I can say that if you plug in 0 for both of these, you're going to get Z1, Z2, right? And yet we see here that at low frequency, the magnitude gain is 0. So I need to write a 1 over Z1 minus 1 over Z2 to normalize this, okay, for the low frequency. Now, because this is second order, and because there's a resonance, it turns out that Z1 and Z2 are complex conjugates of each other, right? And in fact, I mean, you could go ahead and write Z2 is equal to Z1 complex conjugate, blah, blah, blah. But what you should just jump to and say, look, this is going to have the form of s squared plus 2 alpha s plus omega n squared. And of course, the whole thing is going to be over omega n squared because it has to have a magnitude of 1 at the low frequency. You could also write this as s squared plus 2 omega n zeta s plus omega n squared. That works as well. Okay. And the way that you find the value here, or the exact values, is, well, one, you know, because of the peaking occurs at 100, this right here is actually omega n, right? And so you take this transfer function and you evaluate it at omega n, and what you're going to get is you're going to get minus omega n squared for the first term, plus 2 omega n squared times zeta times j, right, because we're plugging in j omega n, and then plus omega n squared, and the whole thing is divided by omega n squared. So now we can cancel some things. These two omega n's cancel, and then this omega n squared and this one cancels. So we end up with h of j omega is equal to 2 zeta j, which means the magnitude of h at omega n, okay, this is at omega n, is equal to 2 zeta. All right, and I'm going to let you work it from here, but the point is, what we found now is that we know the value right here. We're given from the graph, you can find what that dip is, what the minimum value is, and that minimum value corresponds to 2 zeta. So you can solve for zeta, and then you can go back to actually then evaluating what is the second order term. Okay, so make sure that you work through that and you're able to work a second order problem. And it might not be you know, just a second order term. It might be combined with another term as well, potentially.